In this video, we're going to take a look at standard A.11B, which says the student is expected to simplify numeric and algebraic expressions using the laws of exponents, including integral and rational exponents. I'd like to share with you one piece of information that comes from the TEA Mathematics TEK Supporting Information document for Algebra 1. In that document, it says that when paired with A.1a, students may be expected to apply the laws of exponents to scientific notation and real-world situations. I wanted to take a moment to just review what an integral exponent is, and that is an exponent that is a positive or a negative whole number. A rational exponent is an exponent that is a fraction or a decimal. And then I also wanted to review the laws of exponents. So we have the product of powers, which says that if you are multiplying exponents with the same base, you add those exponents. And we have an algebraic example and a numeric example. Quotient of powers says if you're dividing exponents with the same base, then you subtract their exponents. Power to a power, if you're multiplying an exponent and raising an exponent to a power, that means you multiply the powers. And again, we have an algebraic and a numeric example. For negative exponents, we have a rule that says if you have a to the negative n, that is the same as 1 over a to the n. A numeric example, 5 to the negative third is the same as 1 over 5 to the third. It also works if the negative is in the denominator, 1 over a to the negative n equals a to the positive n. Or a numeric example, 1 over 5 to the negative third equals 5 to the third. For zero exponents, any base raised to the exponent of zero is always 1. And then we have rational exponents, what says if we have the nth root of a to the m power, that is the same as raising a to the m divided by n power. I did want to take a moment to discuss zero exponents and negative exponents because students sometimes have trouble with those rules, remembering them. So I feel like if we give them some context and can show them some patterns, it's easier for them to remember. So I actually want to start with, I've listed some exponents here, all with a base of 2 with different powers. I want to start with 2 to the first. We know that 2 to the first is just 2. We know that 2 squared means 2 times 2, which is 4. 2 raised to the third power is 2 times 2 times 2, which is 8. 2 to the fourth power is 2 times 2 times 2 times 2, which is 16. 2 to the fifth, 2 times 2 times 2 times 2 times 2, which is 32. And we could keep going on, but I think this is enough for us for what I want to show you. So if we look, we do have a pattern. We keep increasing by a factor of 2, or if you look, if we were to work backwards or down in the table here, that we are dividing by a factor of 2. 2 to the fifth is 32, then 2 to the fourth is 16, 32 divided by 2 is 16, 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2. So if we continue that pattern of dividing by 2, 2 divided by 2 is 1. This is why anything, or 2 to the 0 power, any base to the 0 power is 1. We're going to keep dividing by 2. So 2 to the negative 1 is going to be 1 divided by 2, or 1/2. So now here we have 2 to the negative 2, which is going to be 1 over 2 to the second, or 1 over 4. And what's 1/2 divided by 2? It's 1/4. So we're going to keep dividing by 2. If we kept dividing by 2, this just shows us again that we would have 1 over 2 to the third, which is the same as 1 over 8. 2 to the negative 4 is 1 over 2 to the fourth, which is 1 over 16. 2 to the negative 5 is 1 over 2 to the 5, which is 1 over 32. So that pattern of dividing by 2 continues down the table. So this is why these rules are true for both zero exponents and for negative exponents. Now let's look at an example for this problem. Simplify the expression 14 a to the 4th, b to the 6th, c to the negative 10 over 8 times a to the negative 2, b to the 3rd, c to the negative 5. So there are several different ways we could attack this problem. So I'm just going to show you one way. But like I said, there are multiple ways that we could do this. So first I'm just going to rewrite what we have here. And if I have coefficients, I do always want to simplify the coefficients. So you can see that we have coefficients of 14 in the numerator and 8 in the denominator. So I'm going to simplify. We can simplify by 2. And we'll have 7 in the numerator and 4 in the denominator. I'm going to go ahead and rewrite that. So now I'm going to apply the quotient of powers rule, which says if we're dividing exponents with the same base, we subtract the exponents. So we're dividing an a to the 4th by an a to the negative 2. So if we subtract those exponents, it's going to be a to the 4th minus negative 2, which is a to the 6th. So we will now have, still have our 7/4. This we have simplified to just give us an a to the 6th. We still have b to the 6th and c to the negative 10 in the numerator, b to the 3rd and c to the negative 5 in the denominator. Again, I'm going to apply the quotient of powers rule for the laws of exponents. And right here we're dividing bases, same base. So that means we subtract the exponents, and that's going to give us b to the 3rd. So we're going to have 7, a to the 6, b to the 3rd, c to the negative 10 over 4 times c to the negative 5. Now I do see that we can do this one more time because we're dividing our base of c, same basis, so we're going to subtract our exponents, so that's going to be negative 10 minus negative 5, which will give us a negative 5. So we're going to simplify this to 7 times a to the 6, b to the 3rd, c to the negative 5 over nothing. Everything is, oh, the only thing we have is, 4 in the denominator. But now we need to get rid of this negative fraction. So we're going to apply the rule for negative exponents to get our final simplified answer of 7 times a to the 6th, b to the 3rd over 4 times c to the 5th power.